So for our last topic of today, we're going to talk about inverse functions. This builds on the last section, so this has to do with a certain special composition of functions. But before I write down the actual definition, I think it'd be a good idea to just write down a small example. So let's just make up a small example that's only defined on 3 values. So let's say if you plug in 1 into the function f, it spits out a 6. If you plug in 2 into the function f, then it spits out a 5. And if you plug in 3 into the function f, then the output would be a 4. So the idea behind an inverse function is that we want a function that undoes whatever the original function f does. So given a function f, we'll be looking for an inverse function, which is usually denoted by f inverse like this. So if f has these 3 properties, then f inverse would have these properties. It would take the input 6, and it would bring us back to the original input 1. So it's just going to undo what f did. So if f took a 1 and spit out a 6, then the inverse would take a 6 and spit out a 1. And similarly for these other ones, f inverse at 5 would bring us back to the 2, and f inverse at 4 would bring us back to the 3. So it's just going to undo what the original function f does. Now here's sort of a fancy way of writing that in terms of compositions. Notice that for any input that we take, if I feed that through the function f to get f of x, and then plug that into the inverse function, that would be f inverse evaluated at f of x. But that should bring me back to the original input. And that's what we saw in the example up above, so maybe let me write down a small example here. If you plug in 1 into the function f, then the output was a 6. But then we saw that if you plug that into the inverse function, it takes you back to the 1. So in other words, if you compose these 2 functions, it should take you back to your original input. And that's actually how we're going to define an inverse function. So the inverse function is going to be the function that has this property. We need that if you plug in the inverse into the function f, or if you plug f into the inverse, then both of those should cancel out in some sense, and you should get back to the original input, which was x. So this is how we're going to define inverse functions. Now, there is one thing that I want to point out right at the beginning, which is that in order for an inverse to exist, we need each of these outputs to have a single input, or to come from a single input. So for example, if this down here, instead of being a 4, if this were a 6, then we would be unable to define an inverse function, because whenever we got down here and we're trying to define what the inverse did to 6, we wouldn't know whether the inverse applied to 6 would be a 1 or whether it should carry us back to a 3 instead. So we need that each output corresponds to a unique input. And that's a property that's called being one-to-one. So in order for an inverse to exist, we need f to be 1-to-1, which means that each output comes from only a single input. So if f satisfies that condition, then we will be able to define an inverse function. So let me give you an example of a function that is not one-to-one. So we've seen a one-to-one function up here. It's just one such that every output comes from a single input. But for example, if we were to talk about a function like f of x is equal to x squared, then here the graph is going to look something like this. Sorry, that's a little messy. Graph looks something like this. And now I can ask whether each output comes from only a single input. But that doesn't hold for this particular function because we have maybe this point, -1, 1, and we also have this point, 1, 1. Notice that both of these points have the same output. So if I was trying to define an inverse function to this, that would be sort of like a square root. But whenever I try taking the square root of 1, I wouldn't know whether the inverse function should spit out a 1 or a -1. So because this function has two inputs that have the same output, this function is not invertible. And that leads us to what's called the horizontal line test. The horizontal line test basically just says that if you can draw a horizontal line that hits your function twice, then that horizontal line, in this case y = 1, gives you an output that corresponds to two different inputs. And therefore this function is not one-to-one, which means this function is not invertible. So that's basically the only obstruction that we can get to invertibility. So now what I want to talk about is how to find an inverse if a function is one-to-one. So let's talk about two different ways of finding an inverse. So we'll say finding an inverse algebraically. And then next we'll talk about how to find an inverse graphically. So first, let's find this inverse algebraically. Let's say that the function that we want to invert is f of x is equal to x cubed. So our first step is to rewrite this as y as a function of x, rather than whatever original name we had for our function f. So here I would write y equals x cubed. The reason that I want to write it this way rather than with the function notation is now what I can do is I can swap the roles of x and y. And that would give me x is equal to y cubed. So I'm literally just replacing x with y and y with x in the formula that I had up above. The reason that I'm swapping x and y here is that notice that that's basically what the inverse does. So here I had an x value of 1 corresponds to a y value of 6. Here I had an x value of 6 corresponds to a y value of 1. So the inverse function has basically just swapped the roles of x and y. And the same thing is true for these other lines. So 2 goes to 5 will become a 5 going to a 2. And similarly, an input of 3 going to an output of 4 would correspond to, for the inverse, an input of 4 going to an output of 3. So this inverse function is just going to be taking the original roles of x and y and swapping them. And that gives us this technique for finding the inverse algebraically. We can just swap the roles of x and y, and then this new y is going to represent the inverse function. So I'll say solve for new y. So if I wanted to solve this equation up here for y, I would probably take a cube root on both sides. That would give me that the cube root of x is equal to y. And that y value is going to represent your inverse function. So if you wanted to write it using the inverse function notation, I would say that the inverse function should be the cube root of x. So remember what that means is that if you apply this and you also apply the original function f, those should cancel each other out and you should just get your original input x. So if, let's say, you take a 2 and you cube it, that would give you an 8. If you then took a cube root, you would get back to your original input, which was 2. And this works for any input. So if you take any x value and you cube it, and then you take a cube root of that, those will cancel and give you x. This also works if you compose in the other direction. So if you take the cube root first, and then after that you cube it, those will still cancel out to give you your original input x. And therefore, these are truly inverse functions. And by the way, this gives you a way of checking whether these functions that we've generated are actually inverse to each other. You can just plug one function into the other, and if they do cancel out to just give you x, then you know that you found the right inverse function. So that gives us an algebraic way of finding the inverse function. Lastly, I want to talk about graphically finding the inverse function. So I'll say finding inverses graphically. Here I just want to point out some behavior on the graph based on the fact that the inverse is just interchanging the roles of x and y. So let me stick with the same example. So let's say that f of x is x cubed. We know what the graph of x cubed looks like. It's something like this. So if I were to interchange the roles of x and y, then I would just be swapping the x and y axes, which is the same thing as just saying that I want to reflect this picture across that dotted line. So if I just reflect this picture across that dotted line, then this y would end up over here and the x would end up over here, and that would be swapping the roles of x and y, which is exactly what the inverse function is supposed to do. So what that means is that, so maybe let me write this as y equals x. So this is the dotted line y equals x. If you reflect across that line, then you're just swapping the roles of x and y. What that means is that if you want to produce the graph of the inverse function, given this original function, all that you have to do is you have to take the original function's graph and reflect it across that blue dotted line. So if I were to reflect this picture across that dotted line, the corresponding picture that I would get would be something like this. So that's going to be the reflection, so it's sort of the mirror reflection of this original function across that blue dotted line. And this will be the graph of the inverse function. So the green one would be f inverse of x, which is the graph of the cube root of x. So that's the relationship between the graph of the original function and the graph of the inverse function. You can always obtain the graph of the inverse function by just flipping the original graph across that dotted line, y equals x. And remember, the reason that that works is just because the inverse function is essentially just undoing whatever the original function does, which is to say that it's swapping the roles of x and y in the original function. So that was a very quick summary of the basic ideas in this section. I don't expect you to immediately understand all of this. I think you'll definitely need to read over the notes and go through the example videos in addition to this. But I think hopefully this summary video can be kind of useful to you either here at the beginning or after you've gone through all of the